Okay, what I want to do real quick is, I guess it's going to be a topic on like processing data, and I don't really have a better way of wording this, but part of it's going to be dealing with data conversions, and another part is going to be dealing with command line arguments. We're going to start with command line arguments. So I'll just go ahead and swap over the slides and let's take a look. So what I mean by passing arguments, it's akin to what you've seen a few times already. But I've already mentioned earlier that we're not really going to do the typical style of when the application is running. You can do things like I mentioned read. You might see scanf. You might see cin and C++. Just ways of taking in data from the user during the runtime of the application. We're not really going to touch on that. Often when you're doing systems level applications, you do it through what we call command line arguments. And you've already seen it a few times. Something like ls has the flags of like -l, -g, -a. This is taken in as an argument to that application. Or if we're doing cat or echo and whatnot, you'll pass in the actual file name or the path to a file or a directory or something. And that will be the actual argument being passed to your executable. That is essentially what we're going to touch on right now. So that is handled at the instantiation of the main function. That is honestly one of the most important parts of any C program. And a lot of time what you've seen in the past is probably just this int main open close parentheses. So just there's no arguments to the actual main function, it's just an empty one. Perfectly fine. If you've been online and you've seen enough of this, and maybe you've done it yourself already, you'll know that we have the options of argc and argv. Argc being an integer, where argv is an array of character pointers, or essentially a string. So argc is our argument count. It's the amount of entries passed to the program. Argv, the argument vector, an array of character pointers that contain each entry passed to the program. Argv0, for example, will always contain the executable name. So you're always going to have at least one argument vector entry. Your argument counter, or argument count is always going to be 1 at the very minimum because you are going to have to call the actual application. Anything beyond that will just be populated in the argument vector beyond like 1, 2, 3, however many you actually have. We can use argc as a means to kind of, I guess, validate a specific amount of entries that have been passed. So if you need at least 3 parameters being passed into the actual application, you can say, hey, if my argument counter is less than 4, we can't run this application because you're going to try to process an argument that doesn't exist. So you can use this as a means of validating what is actual proper methods of executing the program itself. So I have here an example of reading from a file. On the left side, over here, is the actual interface of the file, and on the right side in these 2 blocks here, that is going to be the actual program itself. So if I look at, let's just look at the actual code itself first. I have all my standard headers and whatnot. My buffer size of 1024 bytes, the input buffer itself, and then I have if argc is less than 2, I'm going to throw an error of too few args, and I'm going to exit the program. That means, hey, if I didn't pass in an argument, like an external argument beyond the actual executable name, we're not executing this program. We're cutting it off here. So that's done there. Once we validate we have that, I open argv1. Remember, that is the file path, and it is a character array essentially, so I can use the argv entries directly right there. So I just use argv1 as the actual file path itself. I'm opening it read only, and that is my file descriptor 1. And if that equals -1, I throw p error for open for read. It errors out because it wasn't able to actually open it, and we halt the program. Not a big deal. From there, we're just going to do our typical read file descriptor 1 to the end buff of buff size, get the actual length and number of bytes that were read, place a null terminator at the end of that, close the file descriptor. If I errored out, so if end length right here is -1, there's P error of reading the file, so we'll halt the program. Otherwise, if everything went fine, we're just going to write that out to the standard output stream, and then we just exit with success. So honestly, not a whole lot going on. Main thing is, we have the, we have the argc and argv here. I have some validation using argc that must be at least 2 here. And then you can see I have argv1 being actually used as what is being opened, the actual file name. If I look on the left side, I have my compilation step that's just passing my source code to GCC, naming it read file. So this file name is actually important. I have /read file that is executing what I just compiled, and I'm passing in /sample.txt, so a text file in my current directory. So all it's going to do is just read 1024 bytes from that file and print that out to the user. It's like a very, very limited version of cat, essentially. If I were to loop through it to read it until the end of the file, this would just be implementing cat directly on a single file, of course. So it just prints out hello from sample.txt. I do it again, but this time instead of doing sample.txt as my parameter, I now use testing.txt, using the exact same read file that I compiled in this step right here. So it's the same application. The only thing that's changed here is the actual command line argument that I'm passing in. And now it says hello from testing.txt. So what we've done here is we've created a dynamic form of way of choosing what actual file we want to process. It doesn't change the actual source code whatsoever, because we're not statically reading a file. We're not specifying the file name in the application. I'm specifying I want to read whatever is populated in argv1 here. If I used argv0, that would actually reference the read file executable name right there. We don't want to do that. So that is the command line argument section right there. The rest of this is going to be, how do we deal with integer data types, or numeric data types essentially? Because as we've seen, argv is an array of character pointers, so we basically have a list of strings. Well, if I try to do any arithmetic on that, it's not going to compile, because you're going to try and do this character array divided by another character array or plus a character array. It's not going to be what it needs to be. We need actual integer data types. So we need a way to actually convert those character arrays or strings to the data types that we want. There are multiple ways of doing this in standard C. One very common one that you will see is called A to I. We are not using this. That is not considered thread safe at all for some of its underlying functions, things like this. Those are going to be exempt from a lot of systems level programming. So what we use instead is this scanf. You might say, hey, we already said that we're not using this. No, we're not using scanf. This reads from the user. This does not do that. It has a very similar name, but it is going to allow us to essentially manipulate some data and repurpose a few things. So we'll get to that in a second. On the converse of that, we need to convert our integers back to strings if we want to write that to files or back out to the user, which is still writing to a file, but the standard output stream. So for that, we'll use what's called snprintf. This is very, very similar. So we have scanf, which lets us go from, say, char star to int. And then if I want to do this the other way around, I would use snprintf, which goes int back to char star. That's kind of the idea that we're going for here. Let's just kind of like flexibly manipulate our data back and forth between being character arrays to numeral data types back to character arrays. And they're kind of converses of each other. They work very, very similar. You might be wondering, hey, well, why is there an in here? Well, as a note, since we're using that, rather than the typical sprintf, for safety reasons, we use snprintf because snprintf allows us to specify the maximum number of bytes that we want to actually use, and that lets us prevent an actual overflow. So buffer overflow here is not going to be allowed because we can actually dial in the actual number of bytes that we want to use. There is no snscanf if you're wondering. There is a scanf, sprintf, but they realized this is not safe. So they made a modification to it called snprintf now, and this one is perfectly fine to be used. So first, we have scanf, and it allows us to extract and convert data from strings. So we have kind of some weird parameters here. So we have two guaranteed ones. And you see we have an ellipses here. So the first one above is just the input string to format. It needs to be a null terminated to work properly. So if you've been wondering, like, why do I keep making sure that things are null terminated? What's the purpose of that? Certain system calls and functions require a null terminated string to work properly. This is why. This is a safety feature. You don't have that null terminated string, it's not going to have a place to actually, well, I guess terminate. So it's going to keep on trying to read. The format FMT here, that is very similar to if you've used printf, where we have these placeholders and whatnot. That's how we're going to format the actual string itself. That's going to be where we actually do our conversion process. Beyond that, this is the variables where the values will be stored. So we're not limited to one at a time here. I'll kind of talk about that a little bit later. At the end, we have returned the number of input items successfully matched and assigned. That kind of goes hand in hand with this, where if you have multiple items that you want to convert, you can do them all in one call, and it'll return the number that was successful upon doing that. So if I look at my code here, I have a char star val string of 226. I'm just initializing a string of 226 directly right here. If I wanted to, I could use a command line argument and take this value in from the user. Perfectly fine. For now, I'm just doing a simple static string because it's pretty simple to work with. The next thing I do is I just initialize an empty integer. I call it valInt, so value integer. A format string to integer and store using its reference. So scanf here is going to use this input buffer of my string 226 here. My actual format string is just %d. That is going to be a decimal integer value, so it's just, you know, anything that's like a 10 or a 15. It's not floating point. It's just your basic standard integer. In this case, 226. And then we use @valInt because this is where we want to store this value 226. It's going to store the string, convert that to an actual integer. That's the actual format specifier. And it will populate it using the actual reference back to the integer that I initialized here. Now, we set string using conditional operation. This is just what I'm doing for the actual output. I've already done the conversion process in this one line of scanf here. So when I actually want to write that back out, you can see that I can actually do math with that value integer now. So I have char star out because I just want to print something to the user. And now I can do math. I have val int modulo 2 equals 0 in a conditional operation. So if this math here is true, then we will set out to even with a new line. And if it's false, then we'll set it to odd with a new line. This is basically an if-else statement in a single line if you're not familiar with this, but I'm just doing this to specify what this string is. But the whole point is I can use val int with actual proper data. I can convert this string to an integer data type and do work with it. So in this case, I write to the standard output my actual string, and I just use string length out just because I just want to print the entire string. So what would happen here is I've created the string of 226. It's a character array. I initialize just an empty integer because I want to take the converted result and I want to store it in this reference. So once I run scanf, or scanf specifically, it is going to take that 226, convert that to an integer, and store it in value integer. Next step, I just do this process, which is determining is the value even or odd. 226 modulo 2 has no remainder, so it is even. It is true, so it sets out to even, and then I write even out to the user. If this was 227, it would be odd because it'd have a remainder of 1, so I can actually do some dynamic results using string data. On the other one, we have s_printf, which is used to format a string, very, very similar to how basic printf works. It's similar to scanf to a degree. We're dealing with a lot of those same placeholders like %d, %s, and stuff like that. So if you're familiar with printf and everything of that nature, this should come secondhand to you. So again, we have very, very similar ones. We have the buffer, the format, but this time we have an actual size. This is the number of bytes that we want to actually be written to our output, or the actual string that we want to create. So this is kind of very similar to printf, in which case it formats a string and prints that to the user. This just creates the string essentially. It doesn't print it out to the user. It just creates it in memory, and then we can do whatever we want with that. So same thing with those ellipses variables as well. You can do this for multiple things. I actually do that right here to a degree. So that's for the actual placeholders. Very similar to printf. Returns the number of characters that are written to the buffer if the buffer is large enough. Otherwise, it will just return the buffer size. Okay. Buffer size 1024. That's not going to change right now. We have an output buffer that we want to use. I'm using the actual integer value of 226 this time. It is not a character array. This is just an actual integer. So this is the exact opposite of what we just did. I do char star result is the value passed in even or odd. Same conditional operation. I just don't need to do scanf and all of that nonsense because I'm just working directly with integer data. What I want to do here is I have an integer out length because I need the actual length of the numbers that are written, so I can use that whenever I'm printing out. s_printf, my output buffer, the whole buffer size, that's perfectly fine because I'm using that. I know I can hit up to 1024. That's safe. This just gives you the ability to specify a maximum size so you don't do buffer overflows and whatnot. My format string is %d is %s. So basically an integer is some string. The %d will be replaced with whatever's in val. Again, that is 226. And then %s will be replaced with whatever's in result, which can be even or it can be odd. In this case, I did 226 as an even value. So I'm going to print out to the user in this write statement is to the actual standard output, outbuff, which I am setting using my s_printf. I am saying 226, that's a %d, is, again, just for the rest of the string, that %s will be even, and then /n, of course. then we exit. So if I did value of 227 instead, then value would be 227, so %d would now be replaced with 227, is, in this case, result would be odd. So that's scanf and snprintf. They're honestly not too bad. Now, I do also have a sample of these working where we're writing to a file. So let me see. We have, again, the same thing. We have the code on the right, and we have the implementation on the left. And this is doing some verification, whatnot. Let me see. Code. Okay, let's do this. Code. This is result. This is, I'll call it interface. There we go. That's it. This is me actually running and executing the program, compiling and all that good stuff. This is the actual results. I'm just using cat to print the data of the file that I'm writing. And this is the actual code itself. That's what's going on here. So let's start over here on the code. Again, 1024 byte buffer size. Not a big deal. You can see that we're using argc, argv this time. I am creating argv1 this time, so we can actually create the file. We're all using brand new files. It'll be all truncated, all that good stuff. 644 permissions. Nothing too crazy here. Loop through any remaining argv entries. So I have multiple arguments going on this time. So for int I equals 2, because again we have argv1 as the actual file name, so it looks like we'll have the I'll just call it a.out here, and then I'll just call it out.txt. That's my file name I'm gonna write to, and then it looks like I'm gonna have some numbers. So 1, 2, 3. I have any number of additional outputs. Doesn't look like there's any limit to the parameter size. So I is less than argc. Yeah, it's gonna go through 2 until the end of the argument count, and then I++. So I'm just incrementing these at a time. So integer value, that is just an empty integer because I have scanf for later, and I create an output buffer right here. So these will be used later. I do scanf to read, let's say that my current one is I here, and then I'll increment to my next I, and so on and so forth. So I'm incrementing through these with argvi, %d and val. That's just going to read whatever is at that current argument, store it in this loop's instance value. I then use the same conditional operation I've been doing the whole time, char star result value modulo 2 equals 0, even or odd. And I do s and printf, because once I get all these results that I want, I will format the string that I want to write to the file, just like I did on the previous one, where some number is either even or odd. I'm just now reading those numbers from command line arguments. So I need scanf and snprintf this time. And then instead of writing to the standard output, I am writing to the file descriptor 1, which is the file that was passed in via command line argument. Then we close the file, once we're done with it, and then we just exit. So if I look on the far left side over here, my interface, I do my execution step of /write file. And this time I write file from executable, that's argv0. argv1 is sample1.txt. It looks like I'm passing in 3 numbers, 234, 67, 1265. I run this again with sample2.txt. I run 12, 654, 67, -65. And I run it one more time of sample3.txt, 1 through 7 here. So in the middle, I have the results. I'm just simply using cat to print my results. So I have 234 is even, 67 is odd, 1267 1265 is odd. Second result is 12 is even, 754 is even, 67 is odd, negative 65 is odd. And then, last one is 1 is odd, 2 is even, 3 is odd, 4 is even, 5 is odd, 6 is even, and then 7 is odd. So there's no limitation in this particular program to how many command line arguments I have. It's going to handle this loop the exact same way. I am reading the numbers in, passing them to scanf to get them to be an integer, using my conditional value to actually process that integer data, and then I'm converting my results back to an actual output string to write to my files. So that is the idea of, again, that's why I call this processing data essentially. I really do hope all of this made sense. I hope the command line arguments make sense, because that is a pivotal aspect of understanding how some systems application works, because you're trying not to interrupt any low-level program that's working at the same time. Generally, you want to preset the data that that application is going to run before its execution point, because if you have like let's say an application running at the operating system level and it just all of a sudden halts and asks you for input, that would be kind of alarming, honestly. That's not a good interface that you'd want to work with. Generally, if it is running at low enough level, it needs to have all of its data passed into it when it's executed. That's just the general kind of paradigm that we go for. So understanding command line arguments is pretty paramount there. Beyond that, this is a signal safe way of trying to deal with string to integer conversions and then back and forth, so vice versa essentially. That can be very, very, I guess, frustrating / difficult depending on how you do it. But scanf, snprintf are very good kind of mirrors to each other. If you need to pull data in the form of a character array, so especially the things that you are passing in via command line arguments, taking it to scanf to actually take that data and pull it over to an integer that you've initialized by its reference, and then using snprintf to take that integer data, put it back into an actual output string. They work in tandem very, very well. So, all that being said, I hope this made sense. I hope it was helpful. Hope you learned something. And I'll see you next video.